Question 16. Sketch the graph of the curve y equals negative x cubed plus 3x squared minus 1, labeling the stationary points and the point of inflection. Do not determine the x-intercepts of the curve. The function is a polynomial with degree 3. And the degree represents the highest power of the variable in the polynomial and defines the overall shape of the curve when graphed. So since the degree is 3, the shape is cubic. Now one point that this cubic curve is going to pass through is y-intercept of -1, and that can be found by letting x equal 0. Now let's consider the shape of the curve for large values of x and for small values of x. So as x approaches infinity, so x gets really large, y gets really small, y approaches negative infinity, and vice versa. As x approaches negative infinity, y will approach infinity. And that's because of the negative sign here, this is the leading coefficient, of the term that contains the degree. Now let's find the first derivative and the second derivative because they will be required to find the stationary points, determining their nature, and also to find the inflection point and test it to make sure that it is in fact an inflection point. So y dash, the first derivative, is equal to negative 3x squared plus 6x. And equation number 2, this is the second derivative, so y double dash is equal to negative 6x plus 6. And we find that by differentiating the first derivative. Now to find the stationary points by solving, y dash equals 0. So just by making the first derivative here equal to 0 and solving for x. So we have negative 3x squared plus 6x equals 0. And dividing both sides by negative 3, we have x squared minus 2x equals 0. Factorizing out x, we have x outside of x minus 2 equals 0, and therefore x equals 0 or 2. Now at x equals 0, y is equal to -1, so we substitute 0 into the original polynomial there, original function, y equals -1, which also happens to be the y-intercept. And the second derivative is equal to 6, so that's to determine the nature of this stationary point. And because the second derivative is positive, this stationary point, 0, -1, will be a minimum. And at x equals 2, the y-coordinate of this point will be 3. So substituting 2 into the original function, we have y equals 3. And the second derivative at that point, so using equation number 2 here, that's equal to -6. And because the second derivative is negative, this point, this stationary point, will be a maximum. So we're going to have two stationary points, 0, -1, which is the minimum point, and 2, 3, which is a maximum point. Now to find the point of inflection. And that can be found by solving the second derivative equal to 0. So that's negative 6x plus 6 equals 0, so therefore x equals 1. But we need to test to make sure that it is in fact an inflection point. It's a possible point of inflection at this point. So at x equals 1, y equals 1, so that's the y-coordinate, so that's the actual coordinate of the inflection or the possible inflection point. So let's test if 1, 1 is in fact an inflection point by checking the sign of the second derivative around x equals 1. So we just dodge around it, just with it, not sort of large values of x, but just slightly to the left or to the right of x equals 1 is sufficient. So at x equals 0.9, the second derivative, y double dash, is equal to positive 0.6. And at x equals 1.1, the second derivative is equal to negative 0.6. So there is a sign change of the second derivative around the possible inflection point. Hence, the coordinate 1, 1 is an inflection point. Now we have enough information to graph the function. So here's the y-intercept, which happens to be the minimum stationary point. Here's the point 2, 3, which is the maximum stationary point. Here's the point of inflection there. Okay. Of course, just make sure to use a ruler, draw the axes neatly, label the axes, so x, y, of course the origin, and I tried to draw it somewhat to scale. It's not going to be 100% accurate, of course, but as long as the question is answered, it asked for labeling the stationary points and the point of inflection, and that's it.